I wanted to show you a little demo that I did. I started with the pendulum demo. So this is how you build a pendulum, and this is a line to the pendulum. This is the circle at the bottom. You can see it right here. There it is. And if I start this running, the pendulum swings. You can watch it swing. Now that's a 20-meter string holding onto the pendulum, so it swings pretty slowly. Now what I've added to the pendulum demonstration is two sections. This section here looks at the time. This time is the synthetic time of the window. It's not real time. And I put a series of sample and holds in here, and what I do with that is I can capture values and sort of push them along. And when I capture the value when the pendulum swings from one side to the other, so this says greater than 0, what that means is that when the pendulum crosses from this negative position to the positive position, that's when it goes through the 0, it will trigger these samples and holds. So what will happen is each time it crosses there'll be a value here, and the next time that value will go out to here. If I subtract those two values, I can get the elapsed time, and that's just what this guy here does. Okay, so in addition to the elapsed time, I added this circuit down here. This is pretty simple. It takes the length of the pendulum and runs this equation, which is the period, the time period of a pendulum with gravity. So I'm using the Earth's gravity, and the equation tells us how long it takes for the pendulum to swing one full cycle. So right now at 20 meters, this should be 8.97 seconds. So let's run it, see what happens. So I'll reset and start. Now one thing you should know about that equation is that it's for pendulums that are swinging small angles. And the reason for that is that the force of gravity is pulling straight down, and basically it's the sine, the force on the ball is the sine of the angle, and for small angles, sine is equal to the angle, as long as it's in radians. So when that's true, the forces will come out to be uniform, and there'll be a constant force of gravity swinging this thing back and forth, and everything is wonderful. If the pendulum swings a larger angle, that force changes and that equation no longer holds true. So we have our first result here, 8.98 seconds as opposed to 8.97 seconds. Now my delta t in this simulation is 10 milliseconds. So you wouldn't expect the reading to be any more accurate than that last place there. Let's see what it is this time. Okay, there we go. Now we've got another 8.98. So if we change the length of that rope, let's go faster now. So if I make the rope, say, instead of 10 meters, maybe I'll make it 5 meters. Now what's going to happen here is there's going to be more computational error, but we'll get our results faster. Prime the pumps there. So this should be 4.48 seconds for the elapsed time, and we'll see what we get. 4.49. So we're not that far off, even at this rate. But let's try swinging it further. So what I'm going to do is change the starting position, which is this here, starting angle, and I'm going to make it, I don't want to get crazy here, but let's make it a little bit larger. How about that? So that angle is substantial. So let's go back to watching our elapsed time and get everything positioned here for you to see. Okay, so here we go. Reset and start. Remember, the first time it shows the time here, it's really nothing. It takes time for the value to percolate through that set of samples and holds. Okay, so we should get our first reading now. And you can see now we're off by 0.2 of a second. And again, 0.2 of a second. Okay, so that demonstration was to show you how to calculate, simply calculate using the equation, the period of a pendulum, and how to actually measure it using simulation of the entire motion of the pendulum, including cosine effect. And so and with this we would be able to calculate a pendulum that's swinging larger angles by using this kind of simulation with a timer connected to it.